Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to look at Gaussian elimination with partial pivoting. So, in this topic, we will review the steps taken to solve a system of linear equations. We will then determine that it is actually important to take floating point numbers into consideration. Given this, we will describe the Gaussian elimination algorithm with partial pivoting. We will look at a few examples. However, then we will describe the algorithm in a much more human-friendly format, the previous version being one that can more easily be implemented in a computer. Having described the more human-friendly format, we will look at many more examples. Now, up to this point, you have seen how backward substitution can be used for finding a solution to a system of linear equations when one exists. That is, of course, if the system of linear equations is in row echelon form. Now, you know that there may be either one unique solution or infinitely many solutions if a solution does exist. Next, in the last topic, we described row operations. We are going to use those row operations to try to convert an arbitrary augmented matrix into one that is in row echelon form. Once it's in row echelon form, then we can go back to using backward substitution to find the solutions, that is, if they exist. Now, in secondary school, when solving a system of linear equations, you did whatever was easiest. Suppose that you were given the following system of linear equations. Easy enough. At this point, you'd say, well, at least in this course, what you'd actually do is convert this back into a matrix. So this is the same system of linear equations, but as an augmented matrix. And then what you do is you would add 3 times equation 1 onto equation 2, or equivalently, you would perform the row operation of adding 3 times row 1 onto row 2. So, as a system of linear equations, we now have these two, and as an augmented matrix, we have this here. And in either case, we can determine that, yes, x2 must be 0.9, and substituting x2 into equation 1 using backward substitution, we get that the solution to x1 is 5 minus 1.8, or x1 is 3.2. So that is our solution vector. Now, as an engineer, you must be aware of the tools you are using. A computer is always going to use floating point numbers. That is, it will represent every real number as a finite approximation. So only a fixed number of digits will be stored. Basically, this means when you store a real number on a computer, the best you get is approximately 16 significant digits of precision. Now, that might sound like a lot, but you're going to have to remember that as an engineer, you're actually going to be performing lots and lots of calculations on huge systems of linear equations. This is going to lead to problems, and if you do not mitigate these problems, you will get the wrong answer. As an engineer, you will be responsible if you misuse your tools and get the wrong answer. No one cares that the floating point numbers gave you the wrong answer. They will care if the design you have does not work. So, suppose your computer can only store 4 digits of precision. In this case, if you try to store this as a real number, the best you could do is store it as 5.923 times 10 to the 7. if you tried to store this number, the best you could do is store it as 7.919 times 10 to the negative 4. And the best that you could approximate pi as is 3.142. Not a great approximation, but at least it's an approximation. Also, every time you performed any form of calculation, the result could only be stored to 4 significant digits. So if we were to add these two numbers, each stored as 4 significant digits, well, you could add the two together as we see here on the right, and then we could only store those numbers to 4 significant digits. So even though that is the correct answer, we'd have to store this as 6.011 times 10 to the 7, basically rounding to the closest 4 significant digit number. Let's see where this leads to a problem. If you were in secondary school and given this system of linear equations, you might initially just add negative 100,000 times equation 1 onto equation 2. Alright, that gives you this solution here. It is now in row echelon form, and so you can just use backward substitution. You could solve for x2 and substitute that into the first equation and solve for x1. And you'd get this solution here. Now, it's important to note that this is approximately equal to the vector 1, 1. All right, so this is the correct answer. However, suppose at any one point you were only able to store 4 digits of precision. Okay, not a problem here. I can still add negative 100,000 times equation 1 onto equation 2, and that gives me the following. But unfortunately, those two numbers in the second equation require 5 significant digits to store them exactly. And thus, I'd have to approximate each of them with the closest number that uses only 4 significant digits of accuracy. Unfortunately, in this case, that number is exactly 100,000 or negative 100,000 in both cases. Well, all right, not a problem. That's pretty good. However, if we now solve for x2, we get that x2 is equal to 1. And if I substitute x2 is equal to 1 into the first equation, I get that x1 is equal to 0. This is not a good solution, because you'll remember that the correct solution, if we used rational arithmetic, was that the solution was 1, 1, not 0, 1. However you dice it, 0 is a horrible approximation of 1. All right, is there some hope? Well, suppose we swapped the two equations. Well, if we now swap the two equations, we would now add negative 0.00001 times equation 1 onto equation 2. This gives us the solution we see here. Well, once again, the solutions, or the coefficients 0.99999 and 0.999998 both require more than 4 significant digits to store precisely. If we can only store these to 4 significant digits, well, the best we can store it is as x2 is equal to 1. But that's okay, because now if I substitute x2 equals 1 into the first equation, I get the solution vector 1, 1. Well, actually, that's a really good solution, because to 4 significant digits, that's as close as we can actually get to the right answer. Because the right answer here, stored to 4 significant digits, is indeed 1, 1. So, what happened here? Well, in the first technique, we added a huge multiple of the first equation onto the second. This had the effect of swamping out any information in the second equation. For example, here, if I added that first number onto the second number, I get that solution down there. But if I now store that sum as 4 significant digits, notice that the first number doesn't change. It's sort of like x plus y is equal to x, even though y is not equal to 0. How do we solve this problem? When we perform a row operation where we are adding a multiple of one row onto another, we want to guarantee that we are not adding a huge multiple of one row onto the other. Instead, we want to guarantee that the multiple of one row that we're adding onto another is less than 1 in absolute value. That is, we want to guarantee that the absolute value of the scalar that we are multiplying row I by is less than 1. Basically, this will ensure that the multiple of row I does not swamp out the information in row J. Important! In this course, you do not have to understand the subtleties of working with floating point numbers and the issues involved therein. All of this is going to be covered in a future course on numerical analysis and numerical methods. In this course, you will only need to be aware that there are issues when using floating point numbers, and that the algorithm presented mitigates the weaknesses of floating point numbers. That's all. So we are going to introduce the algorithm that is called Gaussian elimination with partial pivoting. This is an algorithm that is numerically stable. It is going to be different from any implementation taught in first-year mathematics-based courses. Thus, do not look this up online unless you explicitly also search for the term partial pivoting. So here's the Gaussian elimination algorithm with partial pivoting. Let AB be an m by n plus 1 augmented matrix, meaning that A is an m by n matrix and B is a target vector that is m-dimensional. Recall the left arrow means we are assigning, in this case, the indices I and j initially the value 1 each. We will update these indices throughout this algorithm. Now, we check column J. If column J has no leading non-zero entries, all we do is update J by incrementing it by 1. That is, all we're going to do is move on to the next column. However, if column J has at least one leading non-zero entry, we will find that row K that contains the largest in absolute value leading non-zero entry within column J. Alright, so having found that largest in absolute value leading non-zero entry and determined that it is in row K, then what we will do is we will swap row I and row K. So now the largest in absolute value leading non-zero entry within column J is in row I. What we will then do is examine every other leading non-zero entry within column J and add an appropriate multiple of row I onto that subsequent row so as to zero out that leading non-zero entry. So if A sub Lj is a leading non-zero entry that is not in row I, then if we add negative ALJ over AIJ times row I onto row L, then that will have the effect of zeroing out that other leading non-zero entry. At this point, we will increase J by 1, meaning that we're going to go to the next column, and we will also increase I by 1, meaning we are going to go to the next row where we will swap a possible subsequent row so as to place the largest leading non-zero entry to that row. Now, if ever I is greater than m or j is greater than n plus 1, we are done, and the augmented matrix must now be in row echelon form. Otherwise, return to step 1 and run this algorithm again. Now note, that last step is how you would program this into a computer. However, you are able to stop as soon as you see that the matrix that you are manipulating is in row echelon form, because that is what this process will do. So as soon as you see the matrix is in row echelon form, you can immediately stop. Another comment: if you ever find more than one leading non-zero entry that has the maximum absolute value within that column, you are free to pick any one you want. Guaranteed, you will never lose a mark if you pick the quote wrong unquote one. Let's take a high-level overview of how this algorithm will work. Suppose I have a matrix here that has non-zero entries more or less everywhere. So we start with the first column, and we check each of those entries, and we find that one which is largest in absolute value. Wherever that is, we find that row, and we swap that row with row 1 so as to place the largest in absolute value entry into that location. So we just swap two rows. Now we will add an appropriate multiple of row 1 onto each subsequent row to zero each of those entries out. Okay, so now the next step. Going to the next row, we check all the leading non-zero entries. Of course, row 1 can no longer have a leading non-zero entry in column 2 because we already have a leading non-zero entry in column 1. So now we check each of these leading non-zero entries, find the one that is largest in absolute value, and whichever row that is in, we swap that row with row 2. So now that is the largest in absolute value entry within the second column for all leading non-zero entries. We then add an appropriate multiple of row 2 onto all other rows so as to zero all of them out. Now, suppose in this process of zeroing out everything in column 2, we also zeroed everything out in column 3. Well, at this point, there are no leading non-zero entries in column 3, so all we do is move to the next column. We find the largest in absolute value leading non-zero entry in column 4, and whichever row it is in, we swap that row now with row 3 to place that largest entry at that location. We then add appropriate multiples of row 3 onto all subsequent non-zero leading entries within that column so as to zero them out. And we will continue this process on until this matrix ends up being in row echelon form. Consider this 2 by 3 augmented matrix below. So m equals n equals 2. We initialize the indices I and j to be 1. Now, in column j equals 1, there are two leading non-zero entries, the largest in magnitude of which is at index at A22. So therefore we swap row I equals 1 and row 2. Alright, so this places the largest entry in absolute value in row I equals 1. What we will do now is we will add an appropriate multiple of row 1 onto every subsequent row so as to eliminate any other leading non-zero entries in column j equals 1. Well, there's only one other entry there, and that's in row 2. So negative 1.2 over 4 is negative 0.3. So we will add negative 0.3 times row 1 onto row 2. And that will eliminate that non-zero value in column 1. There are no other leading non-zero entries, so we are done. We will increment both I and j. So now we are looking at column 2. In column 2, there is only one leading non-zero entry, and it is already at index ij or 2, 2. So we're done. There's nothing else to do, and you may have already noticed that the matrix is in row echelon form. However, following the algorithm, we would increment I and j, and we determine that I is greater than m, and therefore we are finished. Looking at this matrix, at this row echelon matrix, we can therefore determine that x2 is equal to 3, and substituting that into equation 1, we get that x1 is equal to negative 4.5. All right, so there we have it, an application of Gaussian elimination and backward substitution. Now, consider this 2 by 3 augmented matrix where again m equals n equals 2. We examine column j equals 1 and note that there are two leading non-zero entries in this column. The largest in magnitude is at index 2, 1, and therefore we will swap row I equals 1 and row 2. So that puts the largest entry in column 1 in row 1. We will now add an appropriate multiple of row 1 onto all subsequent rows so as to eliminate any other leading non-zero entry in column 1. Well, there's only one other leading non-zero entry, and so therefore we will add negative 2.4 over 6, and that's equal to positive 0.4 times row 1 onto row 2. And that will eliminate that leading non-zero entry at index 2, 1. All right, and so now we increment both I and j. Next, in column 2, there are no leading non-zero entries. Negative 9 is not a leading non-zero entry, and neither is the 0. So all we can do is increment j. So j is now 3. In column j equals 3, there are again no leading non-zero entries, and therefore we just increment j again. Now j is greater than n plus 1, as j is now 4, and so we are done. We now note that the matrix is indeed in row echelon form. We could have determined that a little bit earlier, but nevertheless, now we see that x2 is a free variable, and then substituting that into row 1, we get that x1 is equal to 0.5 plus 1.5 x2, which is equal to the vector 0.50 plus all scalar multiples of the vector 1.51. Next, consider this 2 by 3 augmented matrix. Again, m equals n equals 2. In column j equals 1, there are 2 leading non-zero entries, but the largest in magnitude is already at index A11, and so the largest entry is already in row I equals 1. Therefore, there's nothing to do. At this point, we simply carry on and eliminate all other leading non-zero entries in column 1. Well, the only one that is left is in row 2, and so we negate negative 2.5 over 5 to get 0.5, and thus we add 0.5 times row 1 onto row 2 to eliminate this non-zero leading entry at index 2, 1. At this point, we increment I and j. All right. In column j equals 2, there are no leading non-zero entries, so increment j. Now, you may have already noticed at this point the matrix is in row echelon form, so you could stop right now. We're done. However, just to show you that the algorithm still works, let's carry on. We incremented row the j, so now in column 3 there is one leading non-zero entry, but it's already in row 2, and there are no other leading non-zero entries in column j equals 3, and so therefore we're done. Increment both I and j. At this point, I equals 3 is greater than 2, which is the value of m, and j is equal to 4, which is greater than 3, which is n plus 1. So we are done. However, now we see that the rank of the matrix A is 1, and the rank of the augmented matrix is 2. Therefore, we have a zero equation. 0 times x1 plus 0 times x2 is equal to 5, which is impossible, and therefore no solution exists. Consider this 3 by 4 augmented matrix. Here, m equals n equals 3. In column j equals 1, there are 3 leading non-zero entries, negative 3.2, 3.6, and 4. The largest of these in absolute value is at index 3, 1, and therefore we will swap row 3 and row I equals 1. So that places the largest entry in column 1 in row 1. We will now add negative 3.6 over 4, or negative 0.9 times row 1 onto row 2 to eliminate that leading non-zero entry at index 2, 1. Simultaneously, we will add the negation of negative 3.2 over 4, or 0.8, times row 1 onto row 3 in order to eliminate the leading non-zero entry at index 3, 1. So that now gives us the matrix we see at the lower right. So we've eliminated all those entries, and therefore we increment both I and j. They are now both equal to 2. So now I and j are both 2. So looking at column j equals 2, there are two leading non-zero entries, negative 3.5 and 5. The largest in magnitude of which is at index 3, 2, and so therefore we will swap row I equals 2 and row 3. That places the largest entry at index 2, 2, and we will now add an appropriate multiple of row 2 onto all subsequent rows so as to eliminate any other leading non-zero entries in column 2. Well, there's only one, and that's in row 3, so the negation of negative 3.5 over 5 is positive 0.7, so we add 0.7 times row 2 onto row 3, and that will eliminate that leading non-zero entry at index 3, 2. Okay, there are no other leading non-zero entries in column 2, so we increment both I and j, which are now both equal to 3. So now both I and j equals 3. So at this point we could stop because we immediately see that the matrix is in row echelon form, and therefore we are finished. However, just to demonstrate that the algorithm does work, we'll carry on. In column j equals 3, there is one leading non-zero entry. It is already at index 3, 3, and so there is nothing left to do. There are also no other leading non-zero entries in column j equals 3, and so therefore we are done. We will increment both I and j. So I and j are now both equal to 4, and we note that I equals 4 is greater than m, which is equal to 3, and thus we are done. Thus, the original matrix is row equivalent to this matrix, and as we can see here, the rank of the matrix is 3, which equals the rank of the augmented matrix, and both of those are equal to the number of unknowns, and therefore there is one unique solution. Performing backward substitution, we find that the solution to the row echelon matrix, which is equal to the solution of the original matrix, is the vector 4, negative 3, 2. Now, consider this 3 by 4 augmented matrix. This again represents a system of 3 linear equations in 3 unknowns. We initialize the indices I and j with the values 1. In column j equals 1, there are 3 leading non-zero entries, the largest of which is at entry a sub 2, 1, that is 5. And so therefore we will swap row I equals 1 and row 2. We will now add appropriate multiples of row I, or row 1 in this case, to all subsequent rows to eliminate any other leading non-zero entries. So we will add negative 1 over 5, or negative 0.2 times row 1 onto row 2 to eliminate the leading non-zero entry at index 2, 1. We will also add the negation of negative 0.5 over 5, which is 0.1, times row 1 onto row 3 to eliminate that leading non-zero entry at index 3, 1. So now we are left with this matrix here. We will increment I and j, so I and j are now both equal to 2. So at this point, we now look at column j equals 2, and we note that there are no leading non-zero entries in column 2. So all we will do is increment j. That is, we will just go to the next column. So incrementing j, j is now equal to 3. Next, taking a look at this matrix, we note that in column j equals 3, there are 2 leading non-zero entries, the largest in magnitude of which is at index 2, 3, and thus it is already in row I equals 2, and so no swaps are required. Next, we will add the negation of 2.7 over negative 9 times row 2 onto row 3, and that will eliminate that leading non-zero entry at 3, 3. Now, we will increment both I and j, and now looking at the matrix, there are no leading non-zero entries in column j equals 0, and so all we will do is increment j. As j equal to 5 is greater than n plus 1, which is 4, we are done, and we do note that yes, the matrix is in row echelon form. Thus, we can now apply backward substitution. However, we note that because the rank of the matrix equals the rank of the augmented matrix, at least one solution exists. But n is equal to 3 and the rank is 2. So 3 minus 2 is 1, therefore there is one free variable. So we will assign x2 to be a free variable, as the second column is the only column that does not contain a leading non-zero entry. And thus we may determine that the solution vector is this vector here. And this is also the solution vector to the original matrix we started back with 2 slides ago. Note, of course, that this matrix can be written as the fixed vector 9, 0, negative 7 plus all scalar multiples of the vector negative 1.4, 1, 0. Now, the algorithm that we described above is one that can be programmed into a computer, and that's something you should try yourself. However, in quickly trying to solve these problems, here is a simpler human implementable version. First of all, the halting condition is easy. Whenever you see the matrix being in row echelon form, you are done. There's no need to carry on. Now, you're going to visit each column within the augmented matrix in order from left to right, one column at a time. Now, the first time you find a column that has at least one leading non-zero entry, you will find that row K that contains the maximum in magnitude leading non-zero entry in that column. Because this is the first time that you've found a column with a leading non-zero entry, we will swap that row K and row 1. You will then proceed to eliminate all other leading non-zero entries in that column by adding appropriate multiples of row 1 onto each subsequent row. Carrying on, the next time you find a column with at least one leading non-zero entry, once again, you will find the row K that contains the maximum in magnitude leading non-zero entry in that second column that has at least one. You will then swap row K and row 2. And as before, you will proceed to eliminate all other leading non-zero entries in that column by adding appropriate multiples of row 2 onto subsequent columns. You will continue this general procedure. So you will continue moving from left to right along the columns, and when you find the third column that has at least one leading non-zero entry, then you'll be swapping a row into row 3, and so on and so forth. At some point you will be finished, and the matrix will be in row echelon form. Alright, let's consider this example here. Starting in column 1, the largest in absolute value entry, that is a leading non-zero entry in column 1, is -3. It's already at location 1, 1, so we're finished. So now all we have to do is add 0.6 times row 1 onto row 2, and -0.2 times row 1 onto row 3. Thus, the first matrix is row equivalent to the second matrix. We proceed to the second column. There are 2 leading non-zero entries, and the largest in absolute value is -5, which is in row 3. Therefore, we swap rows 2 and 3, placing the largest entry at index 2, 2. We now proceed to add -0.3 times row 2 onto row 3 to eliminate the -1.5. So at this point, we could carry on the algorithm, but we do see that the matrix is in row echelon form. Therefore, the original matrix is row equivalent to this matrix, and from this matrix we see there are no solutions, for the rank of the matrix A is 2, and the rank of the augmented matrix is 3. Thus, no solution exists for the augmented matrix in row echelon form, and therefore no solution exists for the original matrix either. Consider this example here. Now, here the first column is already all zeros, so we immediately move to the second column. So we look at all leading non-zero entries in column 2, and the largest in magnitude is in row 3. So we swap rows 1 and 3 to put the largest in magnitude entry in row 1. We now add appropriate multiples of row 1 onto rows 2 and 3 in order to eliminate all leading non-zero entries below that value. So we will add 0.6 times row 1 onto row 2 and 0.4 times row 1 onto row 3. Alright, moving on to column 3, we note that the largest leading non-zero entry in magnitude, of course, is already at row 2. Thus, we do not have to perform any swaps, and we proceed simply to eliminate all leading non-zero entries below that value. So, to achieve this, we simply add 0.7 times row 2 onto row 3. This gives us this result here, and now we can once again perform backward substitution. So, consequently, we see that x3 is equal to -1.2. Substituting that back into equation 1, we get that x1 is equal to 1.5, and the free variable is x1. So note again that we can write this as the vector 0, 1.5, negative 1.2 plus all scalar multiples of the vector 1, 0, 0. Now, consider this 4 by 5 augmented matrix, where the matrix A is 4 by 4 and the target vector is a 4-dimensional vector. We start with column 1. All of the entries in column 1 currently are leading non-zero entries, the largest in absolute value of which is in row 3. Therefore, we will swap all of row 1 and all of row 3. This places the largest in absolute value leading non-zero entry in column 1 at index 1, 1. We will now therefore carry on to eliminate all other leading non-zero entries in column 1. So we will add 0.6 times row 1 onto row 2. We will add negative 0.9 times row 1 onto row 3, and we will add 0.7 times row 1 onto row 4. Thus, this matrix is row equivalent to the matrix we see here now. Okay, so now we carry on to column 2. There are 3 leading non-zero entries. Of those 3, the largest is in row 4, and thus we will swap row 2 and row 4. Now we will eliminate the remaining non-zero entries, so we will add negative 0.4 times row 2 onto row 3, and we will add negative 0.3 times row 2 onto row 4. This now will eliminate the 2 leading non-zero entries in rows 3 and 4. Thus, we are done here. Looking now at column 3, there are 2 leading non-zero entries, and the largest of which is in absolute value is negative 5, and that is already at index 3, 3, so we are done. So we will simply add 0.5 times row 3 onto row 4, and that will give us this matrix here. We see that this matrix is in row echelon form, so we are done. Thus, the original matrix is row equivalent to this matrix, and therefore the solution to this matrix in row echelon form is also the solution to the original matrix. Thus, we can use backward substitution to begin determining, for example, that x4 is 0.4, and using backward substitution, we find that the solution vector is this vector here. Thus, this solution vector is also the solution vector for the original matrix that we started with. Next, consider this 3 by 6 matrix. Here m is equal to 3 and n is equal to 5. We already know that the maximum rank of this matrix is going to be equal to 3, and n minus 3 is equal to 2, so there must be at least 2 free variables. If we apply Gaussian elimination on this with partial pivoting, we start once again at column 1, and we note that at this point the maximum entry in absolute value is indeed in the entry 1, 1. Consequently, no row swaps are necessary. Therefore, we will proceed by first adding negative 0.8 times row 1 onto row 2, and adding 0.3 times row 1 onto row 3. This eliminates all the leading zeros below 2 in column 1. Alright, now normally we would now proceed to column 2, but we note that column 2 does not contain any leading non-zero entries, and therefore we proceed now to column 3. Column 3 has 2 leading non-zero entries, the largest of which in absolute value is at index 3, 3, and therefore we need to swap rows 2 and 3. Okay, now the maximum entry in absolute value is at index 2, 3, and now we will add negative 0.6 times row 2 onto row 3. If we do this, we see, oh, the matrix is now in row echelon form as we have produced an entire row of zeros. We note that the rank of the matrix is 2, the rank of the augmented matrix is still 2, and therefore there is at least one solution. However, 5 minus the rank of the matrix is equal to 3, and therefore there are 3 free variables. And from our backward substitution algorithm, we will declare x2, x4, and x5 to be free. Applying backward substitution, therefore, we get that the solution vector is this vector here, and if we were to write this out, we would see that it is the sum of the constant vector 6.80, 2.600 plus all possible linear combinations of the 3 additional vectors you see here. Next, consider this 5 by 4 augmented matrix, where the matrix A is 5 by 3 and the target vector is a 5-dimensional vector. Now, because the maximum rank of this matrix A is 3, and it may actually be that the rank of the aug matrix could be as large as 4, there's a strong possibility that there may be no solutions. However, we will go through and see what we get. Now, taking a look at the first column, we noticed that there are 4 leading non-zero entries in that column. The largest in absolute value is 5 of row 4, and therefore we swap rows 1 and 4. This places the largest entry in that first column at index 1, 1 as expected. We will now add negative 0.3 times row 1 onto row 2, negative 0.7 times row 1 onto row 3, and 0.4 times row 1 onto row 5. That zeroes everything out below row 1 in column 1. So now we proceed to column 2. There are 3 leading non-zero entries, the maximum in magnitude of which is 8, which appears in row 5. We just finished with row 1, so now we swap row 5 and row 2. So that places the negative 8 at index 2, 2. We now proceed by adding 0.1 times row 2 onto row 3, and we add 0.9 times row 2 onto row 4. And that will eliminate those entries below the negative 8 in column 2. So now we see here at column 3, there are two leading non-zero entries in column 3, the maximum in absolute value of which is again in row 5. Therefore, we will swap rows 5 and row 3 to place that maximum at that location. We will now add negative 0.3 times row 3 onto row 4. Well, that eliminates both entries, so we're lucky. It appears a solution exists because the rank of the matrix now is 3 and the rank of the augmented matrix is still 3, and therefore we can now apply Gaussian elimination, backward substitution, to find that, for example, x3 is equal to 1.5, x2 is equal to negative 1.7, and x1 is equal to 2.5. Now, this isn't entirely obvious, but with a little bit of work, you should be able to deduce that this is indeed true. As you can see, there's a good reason that this is to be programmed into a computer. Now, here is an example of a 5 by 6 augmented matrix. So, m equals n equals 5. So, starting in column 1, we determine that the largest entry in magnitude in column 1, that is a leading non-zero value, which is all of them, is in row 2. So we will swap rows 1 and 2. Next, we will proceed to add appropriate multiples of row 1 onto each subsequent row. So for example, we will add negative 0.7 times row 1 onto row 2, positive 0.8 times row 1 onto row 3, negative 0.3 times row 1 onto row 4, and positive 0.5 times row 1 onto row 5. So that eliminates all those leading entries below that 3. So now we proceed to the next column. Now, taking a look at the next column, we note that there are 4 leading non-zero entries, the largest of which is in row 4. Therefore, we will swap row 2 and row 4. We will now add appropriate multiples of row 2 onto all subsequent rows to eliminate any non-zero values. So, for example, we will add negative 0.3 times row 2 onto row 3. We will add positive 0.2 times row 2 onto row 4. And we will add positive 0.8 times row 2 onto row 5. This will eliminate those 3 entries. Looking at column 3, we find that the largest in magnitude entry, that is a leading non-zero entry, is already at row 3, so we don't have to do anything. Therefore, we will simply proceed to eliminate the subsequent leading non-zero entries. So we will add 0.5 times row 3 onto row 4, and we will add negative 0.9 times row 3 onto row 5. That gives us this matrix here. Looking now at column 4, the largest in magnitude entry that is also a leading non-zero entry in column 4 is in row 5. That is, it is the value negative 10. So we will now swap rows 4 and 5. Having done so, we will now add 0.7 times row 4 onto row 5, yielding this matrix here. We see that this matrix is in row echelon form, and therefore we are done. We can now proceed to use backward substitution to find a unique solution. And how do we know that there's a unique solution? The rank of the row echelon form matrix is 5, and the number of columns in the matrix A is n, or 5. These two are equal, therefore there are no free variables. Also, the rank of the matrix equals the rank of the augmented matrix, so there must be at least one solution. If there is at least one solution and no free variables, there is a unique solution. So, for example, we determine that x5 is equal to 1.3, x4 is equal to negative 0.3, x3 is equal to 4.1. Substituting those three values back into the next equation, we get that x2 is equal to negative 2.3, and this finally demonstrates that x1 is equal to 0.2. Now, the Gaussian elimination algorithm we've introduced with partial pivoting, as we have defined it, is absolutely necessary anytime you program the Gaussian elimination algorithm. We're introducing this right now in 1A, unlike most other linear algebra courses, because you as engineers have to understand there are limitations on the tools you are using to solve real-world problems. And if you do not use the appropriate tools, you will get the wrong answer. All right, that being said, if you are solving a system of linear equations by hand, you are 100% welcome to pick the easiest pivot. So, for example, suppose you're solving this system of two linear equations and two unknowns. At this point, partial pivoting would indicate that you should add a third of row 1 onto row 2. Yes, the computer can do this easier, but by hand, this is almost ugly. So therefore, instead, you could swap rows 1 and 2, and now all you'd have to do is add 3 times row 1 onto row 2. Okay, oh wait a second, this is now easy. x2 is equal to negative 0.6. Substituting negative 0.6 into the first equation has us add 1.2 to the other side, which gives us that negative x1 is equal to negative 0.7, and therefore our solution vector is 0.7, negative 0.6. That's a lot easier, and there was a lot less pain involved. Now, there will be times in this course where the answer is more critical than the technique, and so we will not be always applying the partial pivoting aspect of Gaussian elimination. This is when we are trying to find, for example, eigenvectors corresponding to specific eigenvalues. In class, I will explicitly state any time that partial pivoting is not being used. Now, once again, when you are applying partial pivoting in this class, just to solve a system of linear equations, it will actually make it generally easier. In fact, if you don't apply partial pivoting, it will actually make the question much more difficult. However, there are particular times where partial pivoting will not be used, and you will be made aware of this, and you can choose whichever pivot you deem that will make it easiest for you. So, following this topic, you now understand that we must take floating point numbers into consideration, and therefore you know the Gaussian elimination algorithm with partial pivoting. You can apply the steps these steps to convert a matrix into row echelon form using this algorithm. And at the very end, we did indicate that the partial pivoting aspect is unnecessary for smaller back-of-the-envelope calculations, such as you may be applying in another course just to solve a simple system of 3 linear equations in 3 unknowns. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!